Alright, in this example I'm going to show you how to do linear programming in Python using a program called Pulp. Now the first thing that we're going to have to do is we're going to have to install Pulp into our Spider program. Now this is done using the Anaconda overall data analytics package that we've either downloaded onto our personal computer or we have on the computer in the labs. Now if we're doing this in the lab, we're going to have to do this every single time because the lab computers wipe off each time. If we do this on our personal computer, we're only going to have to do this once. So what we're going to want to do is we're going to want to go to the Anaconda Navigator. So if you search in your computer for Anaconda Navigator, it will launch the entire package. Here it's initializing for us. It'll take a couple of seconds to do that. Get my notes out of there as I'm waiting for this to initialize. And the reason that we do this is we need to access the Anaconda command prompt. Now it opened in the other window, so I'll bring it over here. So when you launch the Navigator, you see all this. This is what we use here, Spider. Typically, I know we just go right into Spider and deal with it there. So what we are going to do is we need to load this program. And that's going to involve doing what is called a Conda Install. So it's a little string of code that we use. So let's launch the prompt. And it'll come up here and it'll look just like an old school Windows prompt. And what we end up wanting to do from there is we're going to have to put in the Conda Install prompt. Now, what you can do is, if you don't want to type this out, is if you come here and you can search for install Pulp, and it will come up here and it will give you the installer. So what we're going to do is, I'm just going to copy and paste this here, but it is Conda Install -C space Conda -Forge space Pulp. If you just copy that and you drop it into your command prompt and hit enter, it will start to collect the data and automatically install everything. And so here, it's going to go through a bunch of things. It's going to ask if you want to install it. I am not going to proceed with this. Typically you would say yes, but this is my personal computer at home. I already have this installed. But you'll just hit yes, you'll run through it, you'll let it install. It'll take a couple of minutes. But once you do that, and I'm just going to close out of this, once you do that, you will be able to access the Pulp files within Spider. And so, as I said, if we're doing it on the lab computer, unfortunately, we're going to have to do this every single time because the lab computer wipes away. You might want to save that little code into a text file that you can easily open up, but it's pretty quick to do. And so let's go, and what we're going to be doing here is we're going to do a linear program. Let's comment this line, linear program using Pulp. And it's technically LP. And this is going to be mirroring example 3.1. And so we'll do some other ones in class, but this is the one that I tried to do a couple weeks ago. And so what are we going to do? Well, the first thing that we need to do is we need that Pulp format. So import Pulp, P-U-L-P, as P. And so what that's going to do is every time that we use P, that's going to be, oh, we know we're using Pulp, and we'll be able to run from that. So what we are going to do is we're going back to that example 3.1 where we wrote out all of our equations to solve this problem. So actually, let me pause for a second here and find my Excel sheet. Alright, so I went and grabbed my sheet that we did in class. These are everything that we wrote down. You should have this within your notes. But we had our decision variables x1 and x2, number of basics computers used, number of XP computers created. Our objective was we're maximizing profit, and our profit equation, once we added all these numbers in, was 80 times x1 and 129 times x2. We have our constraints, which were sell no more than 600 basic computers, no more than 1200 XP. We had our labor constraints between assembly and testing, and we had our non-negativity constraint. So our actual model is we're maximizing 80x1 plus 129x2, subject to all of these constraints here. One of the things that I like about Pulp is everything that we wrote down, we're directly going to put into the model, just like this. Now, Pulp is not the only linear program solver. It's just the one that I'm going to be using here. So let's get this out of the way. Just move that over to the other screen. And so let's start dealing with Pulp. Now, what I'm going to do is we're going to comment this code so we know what's going on. So we are going to create... Got to be clicked on here. We are going to create a LP maximization program, maximization problem with the name, we'll just call it problem. And the objective is to maximize profit. Now we can see, oh, and is, these are all Boolean logic things. It's color coding them. I didn't care about that because I'm going to highlight that, Control 1, and just comment that out so we know what's going on. So the way that we do that is, we're going to actually spell this right with the name problem. And actually, let's call this not just problem, let's call this LP problem so we know it's a linear programming problem. So that case sensitive is going to be important. So we are going to create a variable to stick this all in, and it's LP prob. Actually, let's just yeah, because I don't want to type that out every time. So we're gonna shorten that out. So LP prob, that is our variable, and so we're going to jam into it a function. And that function is going to come from Pulp, and we're going to use the LP problem function in Pulp. So P accesses Pulp, and then we're going to go LP problem. That is a class definition. And so inside of this, we're going to do two things. One, we're going to give it a name. We're going to call it ideal computer mix. I'm putting the underscores in because if I don't, it'll automatically add them anyway. I have it in quotes because it is string. And then the next part, so I've given it a name, and now I have to tell it what we're going to do, and we are going to do a maximize problem. So P, once again, to access Pulp, and we're going to go LP maximize. You can see it comes up there, and we can click on that. We actually don't need... We don't need any of those variables there. So we've created our problem. The next thing that we need to do is we need to create the problem variables. And so not only we're going to do that, we're going to create an x1 and x2 that are non-negative. Control 1 for the comment. And so this is going to take care of our non-negativity constraint as we make the variables. So first thing, we're going to create one variable. We are going to call it x1, and so we need to use a Pulp function, and so we've got LP variable. And so within that, we're going to do two things. The first thing that I'm going to do is I'm going to give it a name, and we're going to say number of basic computers. I'm going to spell it right though. Now, actually, I'm not putting the underscores in here because the problem is if I don't, it's going to just put them in anyway. So let's just go back and put them in. They like their underscores. Now, I used single parentheses here, single double parentheses. Doesn't really matter. It's going to code all the same. And so I do want to add on to that. I could just give it a name and be done, but I want to add a low bound of 0. And that means that it will not allow the variable to go lower than 0, so that puts our non-negativity constraint in. So I am going to copy this line of text because I'm going to use the same line, and I'm just going to change x1 to x2 and number of basic computers to number of XP computers. Because why type that all out again when we can have it just do it for us? All right, so we've created our variables. Those are our decision variables, x1 and x2. So next thing we're going to do is we are going to create the objective function to solve. And control 1, turn that into text. So we already have the objective function written for us, because remember it was 80 times the number of basic computers plus 129 times the number of XP computers. And so if I go and do that, what we're going to do is we're going to take that variable, the LP underscore problem that we did before, and we're going to append it. We are going to redefine it. We're going to add something to it and rewrite it. So if you remember, we talked about plus equals. This would be the same thing as going the new linear problem is equal to linear problem plus something. And so what we need to do is add in that objective function. So in this case, that would be 80 times x1. I have the spaces in there for readability. Do you need that? No, you can just jam it all together. The computer doesn't care. And 129 times x2. Okay, so now we have our variables, our decision variables. We have our objective functions. So with this, we're going to stop this video. In the next one, I'm going to pick up and we're actually going to add in the constraints